गुड आफ्टरनून स्टूडेंट्स। कल लास्ट लेक्चर में हम लोगों ने डिस्कस किया था कैंटिलीवर बीम पर यूनिफॉर्मली डिस्ट्रीब्यूटेड लोड जब उसकी पूरी लेंथ पर हो तो शियर फोर्स और बेंडिंग मोमेंट डायग्राम कैसे बनाते हैं। और कैंटिलीवर बीम हैविंग ए यूनिफॉर्मली वेरिंग लोड व्हेन यूनिफॉर्मली वेरिंग लोड अप्लाइड एट इट्स होल लेंथ। ओके। एंड उसके बाद हम लोगों ने लास्ट टॉपिक जो डिस्कस किया था वो था सिंपली सपोर्टेड बीम हैविंग ए पॉइंट लोड एट इट मिड ऑफ स्पैन। जब किसी सिंपली सपोर्टेड बीम के मिडिल पॉइंट पर कोई पॉइंट लोड लगा हो तो शियर फोर्स और बेंडिंग मोमेंट डायग्राम क्या होता है। ओके। तो उसके आगे आज हम लोग डिस्कस करते हैं। ओके। आज हम लोग डिस्कस करेंगे शियर फोर्स एंड बेंडिंग मोमेंट डायग्राम for a simply supported beam having uniformly distributed load at its whole length. Okay. Now let us consider a simply supported beam AB of length L subjected to a uniformly distributed load W Newton per meter at its whole length. ओके। एक यूनिफॉर्मली डिस्ट्रीब्यूटेड लोड है W न्यूटन पर मीटर जो कि इसकी पूरी लेंथ पर अप्लाई हो रहा है। तो मैंने लास्ट लेक्चर में आपको जैसे बताया था कि सिंपली सपोर्टेड बीम के केस में जब भी आपको शियर फोर्स और बेंडिंग मोमेंट डायग्राम बनाना है तो सबसे पहले स्टेप वन जो रहता है वो स्टेप वन है आपका कि जो एंड पॉइंट्स हैं उन एंड पॉइंट्स पर आपको रिएक्शंस फाइंड आउट करने होंगे, है ना। तो हम यहाँ कंसिडर कर लेते हैं लेट रिएक्शंस एट पॉइंट्स ए एंड बी आर आर ए एंड आर बी, okay, respectively. Now the beam is in equilibrium condition. As we know that the beam is in equilibrium condition. Removing the supports, applying the reactions Ra and Rb, and the distance between the point A and B is L. Okay, here beam is in equilibrium condition, so equilibrium condition. So the algebraic sum of all the forces about the x is equal to should be equal to 0. Algebraic sum of all the forces about y is equal to 0, and the algebraic sum of moment of all the forces about any point should be equal to 0. These three equations should be satisfied if the beam is in equilibrium condition. Okay, here no horizontal force is acting along the x-axis. Along the x-axis there is no force. Only vertical force are acting in UD in this case. Here, as we know that in the case of a uniformly distributed load, we have to convert this uniformly distributed load into point load. Okay, as we know that the weight of a body is passing from its center of gravity point. So in this symmetrical load condition, the total weight of the body due to this uniformly distributed load will passing from its center of gravity, which is at the middle of the span. L by 2 and L by 2. Okay, and the magnitude of this load will be equal to the W into L, because on 1 meter W Newton force is acting, and on L meter W into L load is acting, and this load is passing from the center. Now applying the equilibrium equations, here sigma Fy is equal to 0. So two reactions are acting in upward direction. The algebraic sum of these forces, these upward forces, should be equal to the downward force, which is W into L due to the uniformly distributed load. Equation number 1. Okay, now taking the moment about the point A, taking moment about point A. The moment of reaction Ra about the point A should be equal to 0, because this reaction is passing from the point A. So Ra into 0 is equal to 0, plus next force is acting in downward direction. The magnitude of the force is W into L, and the distance of this load from the point A is equal to L by 2. So the bending moment, the moment due to this load WL about the point A is equal to WL into L by 2, and the nature of the movement is in clockwise direction. So we are taking here clockwise movement as positive. WL into L by 2 equals to the moment of reaction RB about the point A is equal to the RB into L, because the distance of reaction RB from the point A is L, and the nature of movement will be in anti-clockwise, counterclockwise direction. So the movement about the point A of all the forces is equal to this, is given by this equation. So here RB is equal to WL by 2. If RB is equal to WL by 2, Then from equation number 1, Ra is equal to, from equation number 1, Ra is equal to WL minus RB. So Ra is equal to WL by 2. So in the case of a simply supported beam, if the load is applying at the center of the beam, then the reactions at the end points are half of the load. Okay, the reactions at the end points are half of the load. Now reaction at the point A is WL by 2. Reaction at the point B is WL by 2. And a uniformly distributed load is applied, acting at the whole length of the beam. Now step 2 is taking a section between the point A and B, because here load is not changing from the point A to B. Load, uniformly distributed load is acting from A to B. If the uniformly distributed load acting in at some portion of the beam, in that case we have to consider two sections, about the uh, uh, one along the uniformly distributed load and one at which there is no load. Okay, I, now in that case, considering, let us consider a section XX at a distance x from the point A. Okay, now as I already told you that in last lecture, that for whenever we are doing the force analysis of a uniformly distributed load, in that case we have to convert this uniformly distributed load in a point load. Okay, now we have to calculating the force due to the uniformly distributed load acting along the section whose length is x. Okay, the intensity of the load is W Newton per meter. The intensity of load is W Newton per meter. So first of all, we have to let us consider a section XX at a distance x from point A. Okay. Now the shear force about the section XX will be equal to the, here two forces are acting at the left side of the section. One is WL by 2 and another is due to the uniformly distributed load. Now the force due to the uniformly distributed load will be equal to the W into X, because on 1 meter W Newton force is acting, and then on x meters W into x load will be acting, and this force will passing from its center of gravity point, which is at the middle of the section x by 2. Okay, so here the shear force will be equal to plus WL by 2 plus minus WX, because according to the sign convention, upward force should be taken as positive and downward force should be taken as a negative force. So shear force about the section XX is equal to W L by 2 minus X. Equation number 2. Okay, and bending moment about the section XX equal to equal to WL by 2 into X plus minus WX into X by 2. So bending moment about the section XX will be equal to WX by 2 in bracket L minus X. Equation number 3. Okay. Now shear force and bending moment at the extreme points. Extreme points means at at the point A, x is equal to 0, and at the point B where x is equal to L. We have to calculate shear force and bending moment at the extreme points. Okay, first. Now at point A, x is equal to 0. From the equation 2, shear force will be equal to the WL by 2 plus WL by 2, and bending moment will be 0 because x is equal to 0. So at the point A, shear force is plus WL by 2 and bending moment is 0. Now at the point B, X is equal to L. Shear force at the point B will be W L by 2 minus L. So the shear force about the point B will be minus WL by 2. And the bending moment about the point B will be, here X is equal to L, the L minus L is equal to 0, the bending moment, so the bending moment about the point B will be 0. Here shear force is minus WL by 2 at the point B and the bending moment is equal to 0. Here the shear force equation is a linear equation because here x to the power is 1. So WL by 2 at the point A, x is equal to 0, where x is equal to 0, shear force is plus WL by 2, and x is equal to L, shear force is equal to minus WL by 2. These 2 points should be met by a line. Join these 2 points by a line. At the middle of the beam, shear force will be 0. Okay? At the middle of the beam, shear force will be 0. Now, what about bending moment diagram? Here, in a simply supported beam, note that where shear force is 0 or shear force change its sign, at that point bending moment will be maximum. Okay, so at the middle of the beam, bending moment will be maximum because at that point shear force is 0. So at x is equal to L by 2, bending moment will be W by 2 into L by 2 within bracket L minus L by 2. So it will be WL upon 4 into L by 2. So bending moment at the middle of the beam will be WL square by 8. WL square by 8. So in the case of a simply supported beam, when subjected to a uniformly distributed load, bending moment will be maximum at the mid of span, and because bending moment equation is a parabolic equation, so the bending moment variation will be in parabolic in nature about the length x. So the maximum bending moment in the case of a uniformly distributed load in a simply supported beam will be WL square by 8. Okay. Now discussing next topic, a simply supported beam having a uniformly varying load simply supported beam having a uniformly varying load at its whole length. Okay. Now let us consider a simply supported beam having a uniformly varying load at its whole length. The intensity of the load at the point B is W Newton per meter. Length of the beam is L. So follow the step 1 for a simply supported beam. For a simply supported beam, first of all we have to determine the reactions at the point A and B. Let reaction at point A and B are points A and B are RA and RB. Okay. Beam is in equilibrium condition. So equilibrium equation has been followed by the forces Fx sigma Fx is equal to 0, sigma Fy is equal to 0, and moment about a point, algebraic sum of moment about a point will be equal to 0. In the case of a uniformly varying load, we have already discussed that the total load will be equal to the area of the triangle, and the total load will passes from its center of gravity. In the case of a triangle, the center of gravity point is at one third of the length. If we discussing about the base, we are taking base here, then the CG point will be exist at one third of the length from the perpendicular of the triangle L by 3. To L by 3 from the point A, B, and the total load will be is equal to the area of this triangle. The area of the triangle is 1 by 2 base into height, which is equal to WL. The perpendicular is height is W and base is L. So the area of this triangle is 1 by 2 W into L. Now the reaction at the point A is RA and the reaction at the point B is RB. Okay, applying the equilibrium equations for this condition. Sigma Fy is equal to 0. Algebraic sum of all the forces about y-axis should be equal to 0. Here RA plus RB will be equal to WL by 2. Equation number 1. Taking moment about the point A of all the forces, the moment of reaction RA about the point A is equal to 0 because the distance between the force and the point is 0. The moment due to the force WL by 2 will be equal to the WL by 2 into 2L by 3 in clockwise in nature, and the moment due to the reaction RB about the point BA is equal to RB into L. So from here RB is equal to the WL by 3. Now from equation 1 RA is equal to the WL by 2 minus RB, or WL by 2 minus WL by 3. So from here reaction at the point A is equal to the WL by 6. Okay. After determining the reactions at the points end points, the step 2 is taking a section between the points. Okay. Here no load is changing throughout the length of the beam, so only one section is has to be taken between the point A and B. At the point A, removing the supports, applying the reaction. At the point A, reaction is WL by 6, and at the point B, reaction is WL by 3. Total length of the beam is L. Now let us consider a section XX at a distance x from the point A. Between AB. Okay. Now suppose section XX at a distance x from the point A. This is the point D, let this is the point D, and this is the point E. Okay. Okay. So for force analysis of a uniformly varying load, we have to convert this uniformly varying load in a point load. The total load due to this uniformly varying load, which is acting about at a section x at length x, will be equal to the area of the triangle ADE. So suppose the load due to this uniformly varying load acting about the section XX is Wx, and Wx will be equal to the 1 by 2 into base into height 1 by 2 AE into D. Here AE is x, but we have to calculate the value of DE. Now from the right angle triangles, ADE and ABC, okay, because these triangles are similar triangles, then the ratio of sides will be equal to the constant D upon A is equal to the BC upon AB. So from here DE will be equal to the BC is W, AB is L, and A is X, Wx by L. So the load, total load due to the uniformly varying load will be is equal to the 1 by 2 into X into Wx by L is equal to the Wx is equal to the Wx square upon 2s. Okay, this load will be passing from the center of gravity point. The CG, this load Wx square upon 2l is passing from the center of gravity point, and the center of gravity point of a triangle is at x by 3 from its perpendicular. This distance will be x by 3. Okay. Now shear force about the section XX will be equal to the plus WL by 6 plus minus WX square by 2L. Okay. So shear force about the section will be equal to the W by 2 and L by 3 minus X square by L. Okay. And the bending moment about the section XX will be equal to WL by 6 into X plus minus Wx square upon 2L into X by 3. So the bending moment about the section XX will be WLX by 6 minus WX cube upon 6L. Okay. Now we have to calculate the shear force and bending moment at the extreme points. Okay. The shear force and bending moment equation, the shear force equation is a parabolic equation, and the bending moment equation is also a parabolic in nature. Okay. Okay. Now, shear force at x is equal to 0 will be is equal to the, from this equation, from shear force equation, if we place x is equal to 0, in that case shear force will be is equal to the WL by 6. Shear force at the point A is equal to the W by 2 L by 3 minus 0 by L. So the bend shear force about the point A will be WL by 6 in positive term. The magnitude of shear force at the point A, WL by 6. Okay. And bending moment at the point A will be 0. Bending moment will be 0. Okay. Bending moment is 0 at the point A. Now the bending moment at the point at the point B, where x is equal to L, shear force will be W by 2 L by 3 minus L square by L. W by 2 L by 3 minus L. Shear force at the point B will be minus WL by 3. Okay. Here shear force at the point B will be minus WL by 3. Okay. And the bending moment at the point B will be WL by 6 bracket WL by 6 into L minus WL cube upon 6L. Then here bending moment at the point will be equal to 0 again. So in the case of a simply supported beam at the end point, bending moment is 0 in each and every case. Bending moment about the point B is 0. Now bending moment will be maximum where shear force is equal to 0 or changing its sign. Here shear force equation is a continuous equation of a parabola. So these 2 points will meet by a parabola like this. Shear force is 0 at some point. Okay. At this point, corresponding point, bending moment will be maximum. So we have to calculate the distance at which shear force is 0. Okay. Now shear force equation is W by 2 L by 3 minus H square by L. W by 2 L by 3 minus H square by L. Putting this equation equal to 0. So W by 2 L by 3 minus H square by L equal to 0, or say L by X square by L is equal to the L by 3, or say X square is equal to L square by 3. So at X is equal to L by under root 3, shear force is equal to 0. At this point, bending moment will be equal to 0. So bending moment will be maximum. So value of bending moment at X is equal to L by under root 3 is equal to, the equation of bending moment is W L by 6 into X minus W X cube upon 6L. So the bending moment at this point will be W L by 6 into L upon under root 3 minus W by 6L within bracket L upon under root 3 to the power 3. This is WL square upon 6 under root 3 or minus WL square upon 6 into 3 under root 3. Okay. So the bending moment will be equal to the 3WL square minus WL square upon 18 under root 3 or bending moment at the section x is WL square upon 9 under root 3. At x is equal to L by under root 3. This is the maximum bending moment in the case of a uniformly varying load acting on a simply supported beam. Okay, so the maximum bending moment it will be WL square upon 9 under root 3. Okay, so in the case of a simply supported beam, subjected to a point load at x is equal to L by 2, bending moment is maximum and the bending moment, well, the value of bending moment is WL by 4. In the case of a uniformly distributed load at x is equal to L by 2, the value of maximum bending moment is WL square by 8. Here shear force is 0 and here shear force is changing changing its sign from positive to negative, plus W by 2 to minus W by 2. And in the case of a uniformly varying load at x is equal to L upon under root 3, maximum bending moment will be WL square upon 9 under root 3, where shear force is 0. Okay, I hope all the topics are clear to you. Okay, thank you very much.